So we're starting with number 5 here. An astronaut on a spaceship traveling at 0.81 c relative to Earth measures his ship as 30 meters long. So he's measuring the ship in his frame of reference. He eats his lunch in 21 minutes in his frame of reference. So long as an observer on Earth, how long does the lunch take to eat according to observers on Earth? All right. So we're switching frames of reference here. So let's see. This is number 5. Definitely in your Y, you should have that the speed of light is constant from all frames of reference. Okay, do you have your Y? But I'm covering my bases. From all frames of reference, let's say that, what do we want to say? We want to say the Earth and ship, that's an H, are in different frames of reference, right? And is more time. So which one are we going to take as the stationary frame of reference? Okay, because I think because since they're both in inertial frames of reference, we could take either one. Let's take a look. Yeah, but they ask for observers from Earth, so we have to take Earth as the stationary. Wherever we want to observe from is always stationary. So we should add that in here. Earth is stationary. So therefore, less time passes on ship, and the ship will be shorter. That's number 5. You're welcome. So less time passes on the ship, and the ship will be shorter from the Earth's frame of reference. All right. Earth and ship are in different frames of reference. You good? Can I flip to the equation sheet?
Yeah, no,
okay. Well, this will be back up, right?
Yeah.
All right. On our equation sheet, because we're shifting frames of reference, that's our clue that I need the Lorentz transformation. Because I'm talking about different frames of reference. Let's see, I'm talking about how time changes and how length changes. So, I need those. Oops, that's going to mess up. Let's grab this one. And I need how length is going to change. We'll grab that one. So, now that I have those, that's remember how length's going to change. That's how we compare times. Oh, really? It's not having a good afternoon. Let's copy paste this. Then that's Lorentz transformation. All right, so what's the Lorentz transformation's relationship with the number 1? Is it always equal to number 1, always less than number 1, or always greater than number 1? Nope. Always greater than number 1.
Oh, yeah.
Always greater than 1. Because down below, it's always less than 1, which makes the Lorentz transformation always greater than 1. Alright? Something to keep in the back of your mind. That can be helpful. Therefore, we know that t is always greater than t naught. Because if you take a number and multiply it by something greater than 1, you get a bigger number. On the flip side, if I take a number and divide it by a number greater than 1, I always get a smaller number. So L is always less than L naught. So if you can remember that about the Lorentz transformation, then it's a lot easier to make sense of these because from our y, we know less time passes on the ship. So this T naught must be ship time. That makes T Earth time. We know that L is less than L naught. That means L is Earth length, and L naught is ship length. All right, so rather than trying to memorize which way it goes, if you can remember that gamma is always greater than 1, you can apply a little bit of logic. That cabinet's kind of a little bit broken, so if you can resist playing with it, it would be good so it lasts longer. It's okay. It's okay. I know it's hard when you're sitting right there. If you want, grab some tape from my desk and on the inside put a piece of tape to hold it shut. Okay. Alrighty. It is. It's hard. So, let's see, which one do we want to do first? So we were given the ship's time and the ship's length. Let's just look at our answers to make sure. Why don't we do length first? So I'm told that from the ship's frame of reference, it's 30 meters long, and it's moving at 0.81 c. So I'm going to take my length. So that means from the ship, they told me it's 30 meters long, so that's going to be L naught. And my velocity is going to be my 0.81 c. So L is what I want to know. L naught is 30 meters. And then if I divide by gamma, it's like multiplying by the square root. It's in the denominator. 1 minus 0.81 c over c quantity squared. Anything cancel out? The c's. That makes it easier to put in my calculator, right? So let's grab my calculator and put in, let's see, 30 square root of 1 minus 0.81 squared. Enter. Good, I got a little smaller number. That's what I was hoping. So the length of the spaceship as viewed from the Earth would be 17.6 meters. Any questions on that before we move on? You got 2.8. You might have put parentheses in the wrong place. Or you're moving very fast. Remember, the faster you're moving, the bigger the difference in the lengths. Okay, so you have math list. Order of operations. We good to go on to the time? What do you need?
Yeah, it's okay, I got it.
Sure?
Yeah, I got it.
Excellent. Excellent. All right, so now we're moving on to the time. Remember, we have that T is from the Earth and T naught is from the ship. And they tell us, let's see, that 21 minutes passes on the ship. So we're expecting more time on Earth. So we're looking for T. We have T naught as 21 minutes over square root 1 minus our 0.81 c over c quantity squared. And we solve for T. I'm waiting. Well, remember, time is T equals Lorentz transformation times T naught. For the length, it's L equals L naught divided by the Lorentz transformation. That's why here I end up with them multiplied together, the number multiplied by the square root. That's our factor to tell us how to get from that's okay, one frame of reference to another frame of reference. So this says, hey, to transform from one to the other, use this. Right, so like here, when I put in the 1 over the square root thing, that's why I end up with the time divided by that. Here, because the Lorentz transformation is on the bottom, I end up with it multiplied by, because it flips upside down. So, oops, that's not what I wanted. I want to keep this good, and I want to open up my calculator. So I'm doing 21 divided by square root 1 minus 0.81 squared. Oops. Yes. Did they ask? I haven't looked at what units they asked for it in. My units right now are minutes. Right? Because I have minutes up top and then no units down the bottom. Check your operations again. I got 35.8. That makes more. What's your speed, Jeff?
0.7.
Yeah, that. All right, we're going to do number 7, and as someone did point out, it is up in the video, but we'll be quick about it. And number 8 is also up in the video. If you're struggling with number 8 is up in one of the other classes also. Yes, yeah. Because I know in 7 I did it in my honors class in E-block, and I stopped the math early because of one we'd done just before that. So I figured do it again with you guys and go a little more into the manipulating the math around. Make it so you guys got it. All right? I hope I'm recording. Yeah, I am recording. Okay. So we're going to do number 7. We got rocket A passes Earth at this speed. At the same time, rocket B passes Earth, moving in this direction. Same direction, faster speed from Earth. How fast is B moving relative to A when it passes A? So, how many different frames of reference here? Huh? 3 different frames of reference. Good. And we have to decide which one of these 3 we're going to take as stationary, because we get this relative velocity. You know, velocity is going to be different as measured from each frame of reference. So, I'm going to suggest that we take the Earth as the stationary frame of reference. Is that okay with you guys?
Yeah.
All right. So, I mean, we can do it with other ones. So I'm just going to suggest that. So this is 7. We're going to say, I would have definitely in your Y that there are 3 different frames of reference. We have Earth, and we're going to take that one as stationary. We have ship A, and we have ship B. Important to note that C is constant and absolute from all frames of reference. That is one of the major factors to keep in mind here, that there is no way for something to be moving faster than the speed of light. So no matter how these velocities combine, they must always combine to be less than the speed of light. There will never be a situation where it's more. You might even put in here that all velocities are relative to your frame of reference. All right, so they're all relative to your frame of reference. Good. Any questions on the Y? No? All right, so the equation that I need is our relative velocity equation. Oh, come on, hit it. There we go. Which is this one right here. So anytime I know I have relative velocities, this is the equation I'm going to use. A couple things I need to kind of set out before I get going is since Earth is a stationary frame of reference, anything without a tick mark is from Earth's frame of reference. Anything with a tick mark is from, let's see, they want us to measure the speed of B relative to A. So let's say anything with a tick mark is from A's frame of reference. All right? So in our equation, you'll notice we have like U and U prime. That prime is the tick mark I'm talking about. That's what we're going to get to. But so when I'm talking about U, that's going to be measured from the Earth's frame of reference. When I talk about U prime, it's going to be measured from ship A's frame of reference. Yes? You guys good? Yes? No?
Yes.
All right. So now it's a good idea to keep in mind what U is. U, let's say that U is the speed or velocity of ship B. And we'll say V is the speed or velocity of ship A. Yes, but it's good to have V be the one that you want to eventually be measuring from. But it really doesn't matter as long as you pick them. But usually I try to get it so that it's one of the U's that I don't know. And V is a known. And then these are really velocities. I should have vectors over these because we just have to take into account if they're positive or negative. All right. But in this case, everything is positive, right? Rocket A is going this way. Rocket B is going this way. All right. So let's start putting in based on our rules. So we're told that rocket A, which is our V, passes the Earth. So it's from the Earth. It's 0.7 C. So that means that V is going to be 0.7 C. And then I'm also told that B passes Earth relative to the Earth at 0.98. So that means U is 0.98 C. And to be completely correct, I should have a 7.0 C here. And I'm asked to find what U prime is. All right? So, 0.98 C equals U prime plus 0.70 C all over 1 plus U prime times 0.70 C all over C squared. I can't because they're added. I can't get rid of the C's. In fact, I don't want to get rid of the C's. Well, because they asked me, they say find U prime as some number times C, right? They want that box filled in. In other words, they want U prime in terms of the speed of light. They don't want like 2.58 times 10 to the 8th meters per second. They want 0.8 C, 0.9 C, something like that, right? Yes? So, if I want to find the number that goes in this box that's going to be less than 1, what I really want to solve for is U prime over C. That will give me the number in the box. I know, it's Friday afternoon. London, yes? No? Don't say sure if you're not sure. Okay. So here's a little bit of tricky math. I want to be able to solve for u prime over c rather than just u prime because that'll lead me directly to my answer. How does u compare to c? U prime compared to c. So I'm going to do two mathematical steps here. One, I'm going to first multiply both sides by 1 over c. So I'm multiplying this side by 1 over c, and I'm multiplying this side, and I multiply it up top, by 1 over c. All right? Doing the same thing to both sides. Well, if I was to, when I multiply the whole thing by 1 over c, the whole side, I have a choice. I can either multiply the top by 1 over c, or multiply the bottom by c, right? Because of fractions. I'm going to choose to just multiply the top, because multiplication is commutative or something like that. So if I take 0.98c and multiply it by 1 over c, I get 0.98. Then over here, this isn't going to affect the bottom at all, so I'm just going to write that again. At the top, 1 over c times u prime is u prime over c plus the 0.70c times 1 over c is going to be 0.70. Remember, the c's will cancel. Doesn't look much prettier yet, right? False. Well, good thing is we only have one more math step, and then we can easily put it into a solver. All right? The last thing I want to do is distribute out this. Or the last out. Because u prime times 0.70c, if I can distribute out. So let's distribute it out, and I'll do it. I'm not touching the top. The top is all happy now. I'm actually trying to get it into a form that'll be easy to put in Wolfram. But you could. You could have way back up here. But then you would found u prime, and then you would need to divide u prime by c to get your answer. So you could. Yes, you could. Just make sure you put in the value for c. No, I'm telling you the extra step. When you put this in, make sure you put in the value for c. And when you're done, whatever answer you get will be like 2.79 times 10 to the 8th divided by the value of c to get the answer Wolfram. No, it's not. When I have this fraction here, I can distribute out like this. Yes? And then the c's cancel. And I'm left with 0.98 equals u prime over c plus 0.7 over 1 plus u prime over c times 0.7. And I'm going to plug that into Wolfram, but I'm going to use x rather than u prime over c when I put it in Wolfram. I'm going to treat u prime over c as one variable. Right. Sure. Is there another one you like? So I'm doing 0.98. No. Not x over c. equals, parentheses, what variable do you want me to use? X. Because I'm trying to be nice. Plus 0.7 divided by, parentheses, 1 plus X times 0.7. It'll come up again. I did the dividing. And that's going to give me an answer for U over C, which in my case is 0.982. 0.892, excuse me. Yep. So my U prime over C, remember, is the box that I'm trying to fill in, is 0.892. So U prime is about 89% the speed of light. And I bet that's right. Let's see if I got it right. So let me know if you need help. You need to check your... All right, we're going to do number 3. Earth's frame of reference, the star is 80 light years away. How fast we travel, so the distance would be only 38 light years. So in this one, remember the length isn't going to change in the Earth's frame of reference, but in your frame of reference, sitting in the spacecraft, or whatever you're in, you're not moving, the universe is moving, so this star comes close, approaches you. Well, if the universe is moving, then the distance measured in the universe is going to get smaller from your frame of reference. So the star isn't 80 light years away anymore, it's 38 light years. Now you guys understand that a light year is the distance light travels in 1 year. That's what a measure of a light year is. Okay, so it's how far light travels in 1 year. A lot of people think, oh, no, it must be a time thing because it has the word years in it. No, this happenstance. It's a distance. So it's a length, it's a distance, it's a direction of travel. So if we're over here on this, number 3, we start with our C is constant. The ship is stationary, and the universe is moving. And there's more that you could have in there. I'm going a little quick since we're getting close here on time. I'm going to grab, because we're looking at 2 different frames of reference, grab my Lorentz transformation. And since we're talking about one of the physical dimensions, I'm going to grab my length transformation. Looking back to the one we did earlier, what's the relationship between L and L naught? We have 1 vote for L is greater than L naught. Anybody looking back to like the first one we did? L naught is always greater than L. Because remember, gamma is always greater than 1. Dividing by something greater than 1 always gives you a smaller number. So our L, therefore, is our L naught is our 80 light years, and our L, since it has to be less, is our 38 light years. Good job remembering London, by the way. So we have 38 light years equals 80 light years. And if I'm dividing by that fraction, it's like multiplying by the square root 1. 1 minus. Now here's where I'm going to put v over c and square it. Because like last problem, I don't want to really find v. I want to find v over c. Because they ask it from me in terms of the speed of light. So that's really v over c, the numerical answer they're looking for. So I'm going to leave that as v over c and then solve. You could do that in Wolfram. You could also just do a little algebra, right? 38 light years over 80 light years equals the square root of 1 minus v over c squared. Treat that as a single variable. Do you guys think you can do this algebra, or you want me to continue? Well, I'm just going to do a little bit more algebra and then let you take over. Square both sides. Then get when I'm done writing, yeah. What do you need for the problem? Well, why not just flip it back up to here where we established that L must be less than L naught. Use that knowledge. There you go. And then solve for v over c. I'm going to let you do the last little bit of algebra there. But I will try it also to make sure my method works. Yeah, have a good